Hey everyone, and I know it's been a little while. It's been like a month since I last made a video. But now we're back and we're doing some number theory problems I got sent. We have 3 of them, so we're going to be doing them today in my first upload of April. So we have number 1. The numbers p and q are prime with p plus q equals 2018. Compute the least possible value of the absolute value of p minus q. So this is pretty simple. So we know that p plus q is 2018, so let me write that down. P plus q is 2018, which we can then rearrange this equation just to solve for p and q. So p is equal to 2018 minus q, and of course q is equal to 2018 minus p. Now from there we have our, I guess I probably should have written this equation down. We have absolute value of p minus q. We can now plug in our new new definitions of p and q into this equation, and so we would have, we're going to write out 2 of them. So we're going to have 2018, the absolute value after, minus q, and we don't know what this number is, we just want the least possible value of it. We'll just call it x. And of course we also have them plug it in for p. Oh, I just did that. Okay, so now plugging in for q, 2018 or p minus, and 2018 minus q, not minus q. Let me erase that. It should be minus p. Minus p. And of course this is also equal to x. So we can just simplify out these equations and essentially solve for x afterwards, or not solve for x, but make it into linear equation, and from there we'll get the solution. So we're gonna take just the positive version of this. X is already positive, so we're just gonna remove the absolute value signs and simplify this down. So we'll have 2018 minus 2q is equal to x. Same thing here, we don't need the absolute value, x is positive, we're just gonna take it out and we'll distribute this negative, so we'll have 2p minus 2018, this equals x. So from here we're gonna solve for our respective variables here, p and q, to get 2 linear equations, and then we can go from there. So do that, we subtract 2018 both sides, divide by -2. We'll have q is equal to, that's a z, not an equal sign. Okay. Equals, and then we'll have negative x over 2. And then subtracting 2018 and dividing by -2 will get us positive 1009. From here, we'll do the same thing, but for this equation here. So this time we'll add 2018 divided by 2. So we'll have p is equal to positive x over 2 plus, and then still 1009. Now essentially what we're going to do is we're going to have these 2 equations intersect each other, and by doing so we see that our x's, they have coefficients that are the same. They only differ by a sign, meaning that the only place that they'll ever intersect is when x is equal to 0, or their y-intercept. So that means p and q both have to be 1009, which is in fact a prime number, so we're good there. And 1009 plus 1009 is 2018. And so that means the least possible value of p minus q is 0. It's a poorly drawn out 0. My throat hurts, but it's whatever. So this is our answer to number 1. The least possible value of p minus q, absolute value of p minus q, is 0. If I'm wrong, well, it's a competition math problem. and so I'd feel real stupid. I'm very proudly proclaiming that it is 0, but if there's a different solution, feel free to call me out on it. But for now, we're going to say it's 0, and we're going to move on to number 2, which I think is a little easier, or at the very least, I have a less mathematically elegant way of solving it. So let me just erase all this. Okay. So number 2, we have the set of positive integers n minus 2, n minus 1, n plus 1, and n plus should be 2, not 27. Should be ending brackets here, so we'll here. N plus 2 contains no prime numbers, and the sum of these 5 integers is s, which equals 5n. Compute the least possible value of s. So what are we going to do? Well, we need 5 consecutive non-prime numbers, so we're just going to write out a whole lot of numbers. 1, 2, so no, it can't be 2, 3, 4, 5, 6. What we'll notice as we go on is, at least within the first 10 natural numbers, there is like a prime almost every other number, right? 1's not prime, 2 is prime, and then 3 is prime. 4 is good, 5 is not, 6 is good, 7 is not, 8 is good, 9 is good, 10 is good, and 11 is not, 12 is good, 13 is not. So essentially we just have to scale this up until we get into our 20s, mid-ish 20s, and we'll start with 24, because 23 is not prime, or sorry, 23 is prime, 24 isn't, 25 is not prime, 26 is not prime, 27, and then 28. So now we have 5 consecutive prime numbers, or sorry, non-prime numbers, because this 6 times 4, or 2 times 12, 5 times 5, 2 times 13, 3 times 9, 7 times 4, and so these all are non-prime numbers, and as far as I'm concerned, as long as I know how to count, I think these are the earliest 5 consecutive non-primes, where we choose n to be 26, so n equals 26, thereby making n minus 2 24, n minus 1 25, and then n plus 1 27, and n plus 2 28. But from there, we just have s equals 5n, or in other words, s is equal to 130. Exciting. What a fun math problem where you just write out numbers until you get 5 non-primes. There's probably a more elegant way of solving this, but this is probably one of the quickest. Whoops. This is whoops, sorry if I flashbanged anybody, but this is probably the quickest if you don't know any mathematically elegant ways. Just write out your numbers until you find 5 consecutive non-primes. So that's number 2 done. I'll probably add some check marks to say I got this one done. This one's done. This one's done. Now number 3. I like this one. This one's actually a lot of fun. It's asking, how many 6-digit multiples of 11 are in the form 20a times 2018 times b? So reading this question out, I first thought, oh, it's just 2 numbers multiplying 2018. That's not the case. You do not rearrange this equation to be ab times 2018 or anything like that. A and b are essentially stuck there because they need to have the number 2018 in between them. So it's asking, let me write this out, 11x, where x is an integer, so if we want we can do the old x belongs to the positive, we'll say positive integers, and this is equal to a times 2018 times b. We don't need to necessarily solve for this, it's just asking how many numbers, how many 6-digit multiples of 11 are like that, look like this, that have the number 2018 in the middle of them. So this automatically limits down the scope of the numbers, meaning that in between 100,000, so of course this is a 6-digit number, this has to be less than or equal to 11x, or just a multiple of 11, we're just calling it this, and this has to be less than or equal to 999,999. This is the largest 6-digit multiple, or rather just largest 6-digit number you would have before you get into the millions. Not, of course, including decimals, because we're looking for multiples of 11, so these are integers. So because we have this, we also know that a and b can only be certain values, right? We can't have a be 0, because then it wouldn't be a 6-digit multiple, but we can't have b be 0, and the max for either of these is 9. So we're going to write that out too. So 1 is then equal to a. So a is just in between 1 and 9 as a digit, and b well, it gets the luxury of being 0. So from there, what can we do? Let's write out some sample numbers. So if we took 1 and 0 for a and b, we would have the number 120,180. And we have to see if this is a 6-digit multiple of 11. However, that comes out to 90 different combinations, and unless you want to crank out every combination of these numbers and see if they divide by 11, it's not gonna be super fun, nor is it elegant, nor is it very time efficient. So instead, what we're gonna do is we're gonna look at the divisibility rule of 11. So essentially, it takes the sum of the odd digits. So for instance, if we looked at 120,180, the odd digits, that'd be 1, 0, 8. There's these 3 odd digits, so we're gonna add 1, 0, and 8, just comes out to 9. And we're going to subtract the sum of the even digits. So that's 2, 1, and 0. So it's just 3. This comes out to 6. Now, in order for a number to be divisible by 11, the sum of the odd digits, or the difference between the sum of the odd digits and the sum of the even digits, has to equal 0 or a multiple of 11. Now, 6 is not 0, nor is it a multiple of 11, so we can say that 120,180 is not divisible by 11. So we're gonna add some notation, some variables. We're gonna call x1 the sum of all the odd digits. However, actually, let me erase this. However, we know the max, like the biggest number that this multiple of 11 could potentially be. It's if we just took a to be 9 and b to be 9 as well. So we would have 920,189. This is the largest number it can be, where this is a and this is b. Let me write that down. This is a, that is b. So if we apply the divisibility rule of 11, we would have, let's call the sum of the odd digits x1. We're going to call the sum of the even digits x2. And subtracting these two, this has to equal 0 or 11x, a multiple of 11. So knowing this, we can actually say what x1 and x2 can sort of be potentially equal to if we look at the divisibility rule of 11. So for x1, this is the odd digits. We're going to look at 1, 3, and 5. Now remember, this is a, so we're going to have that as a placeholder. We'll have a, because a could be any number between 1 and 9. So a, so we have 1 and then 3, so it's going to be plus 0, so it's adding nothing. And then we'll have 3, 5, so plus 8. So a plus 8 equals x1. Now we look at b, we're going to have this number here. This is the second digit, so it's an even. So we have 2, and just 1, so it's 3. We don't include the others. And this is just b. So b, it's a terribly drawn out b. So we have b plus 3. This equals x2. Now if we plug these new values in for our x1 and x2, we'll have a plus 8 minus, oh, this is b plus 3, and this will equal 0 or a multiple of 11. How do I move? I thought I figured out how to move. Oh, here we go. Here, we'll move here so we have a little more space. I still want to have the problem stuff we wrote out. Here, alright. So now from here, we're just going to distribute the negative and rearrange. So we're going to have, let me select my pen again. We're going to have, so a minus b, and then negative 3 plus 8. So we'll have plus 5 equals, we're going to set this up into two separate equations now, 0 or the 11x. So we'll have a minus b, and I'm just gonna bring the 5 to the other side. So we have 11, x minus 5, and likewise here we'll have a minus b is equal to negative 5. From here, this is pretty simple. I already laid out the numbers that a and b could be potentially equal to, so now we just have to find the combinations that come out to negative 5 for this case. So we're going to start top, the lowest number of a, and lowest number of b, that can bring out to negative 5. So we have 1, 6, 2, 7, 3, 8, and then 4, 9. Let me write out these as ordered pairs. So this already comes out to 4 different combinations that we're going to have for it being a 6-digit multiple of 11. 4, but now we have to consider this. Now, we know our multiples of 11, right? We have 11, 22, 33, 44, 55, so on and so forth. However, these numbers will not subtract to be anything greater than 11, so we don't really have to consider the other multiples. We can just have 11 and then minus 5, so that comes out to 6. So we would have a minus b, and this equals 6. And of course, we can just find all the combinations of a and b that whose difference is 6. So we're going to start top to bottom now for in terms of the values a and b could be. So we'll have 9 minus 3. So 9, 3. And then we will have 8, 2, 7, 1, and of course 6, 0. So all in all, we would have 8 total combinations. Let me write it in big text. Total. I guess not technically combinations. That's not the right word. It's 8 total multiples of 11. 6-digit multiples of 11 that are, of course, since they're multiples, divisible by 11. So that's 8 total multiples. We are done now. So yeah, that's my number theory little smorgasbord mismatch video. It's got 3 problems, and we are now done. We are now done. Thank you for watching.